Picture a postal sorting facility running 24 hours a day. Thousands of packages arrive every hour. Workers process each one, label it, box it, load it onto the right truck. Every package leaves. Nothing sits. The system is built for continuous throughput, and for years it runs perfectly. Now picture the same facility, same packages still arriving, but the trucks have stopped coming. The conveyor belts have jammed. The labels are peeling off the boxes mid-assembly. And because nothing is leaving, the packages begin piling up on the floor, then the shelves, then every surface of the building, until there is no room left to work. The facility is not broken because too many packages arrived. It is broken because the outbound system has completely failed. That facility is your liver, and those packages are dietary fat. Right now, inside your liver cells, there is a molecular shipping operation that is supposed to run continuously, packaging fat into microscopic transport particles and sending them into your bloodstream, where your muscles burn them, your heart runs on them, and your body uses them as fuel. When this outbound system works, fat flows. When it fails, fat accumulates, not because you are eating too much, not because you lack discipline, but because the cellular machinery responsible for exporting fat has been quietly shutting down. And the signal that it is failing is not your weight, it is not your waistline. It is something happening at a scale so small that no mirror, no scale, and no standard blood test will show it to you directly. What is failing is a process called very low-density lipoprotein secretion. And understanding why it fails at the level of the actual molecules involved is the only way to understand why some people's belly fat simply will not move, no matter what they do. If you have ever done everything right, the caloric deficit, the cardio, the clean eating, and still watched your midsection refuse to change, this video explains exactly why. Stay with this, because the answer is not what you expect, and the solution is more specific than anything you have been told before. Part 1. The liver is the fat export engine, not a storage tank. Your liver is the metabolic command center of your entire body. Every gram of dietary fat you eat eventually arrives there, packaged inside tiny transport vessels called kilomicrons, assembled in your intestines, and delivered through the lymphatic system. The liver receives that fat, breaks it down, and then makes a decision: burn it for energy, export it to other tissues, or store it. Under healthy conditions, the liver stores almost nothing. It is a processor, not a warehouse. It takes the incoming fat, repackages it into transport particles called VLDLs, very low-density lipoproteins, and secretes those particles into the bloodstream. From there, the particles travel to skeletal muscle, cardiac muscle, and other tissues, where an enzyme called lipoprotein lipase breaks them open and releases the fatty acids for oxidation. The fat is used, the liver is clear, the cycle repeats. When the VLDL export system fails, none of that happens. Fat arrives at the liver and stays there. Triglycerides accumulate inside individual liver cells, hepatocytes, as lipid droplets. The liver swells. Its capacity to process new incoming fat degrades. And the fat that should be fueling your muscles sits inert inside an organ that has been transformed from a high-throughput distribution hub into a stagnant reservoir. This condition has a clinical name: hepatic steatosis, fatty liver disease. It now affects more than 1 in 3 adults in the developed world, most of them undiagnosed, most of them blaming themselves for a problem that has nothing to do with discipline. Protocol: liver health baseline. Ask your physician for a liver ultrasound if you carry central adiposity and have not had one. Request a full lipid panel and ask specifically about your triglyceride to HDL ratio. A ratio above 3 is a direct clinical signal that VLDL export is impaired. Ask for an ApoB measurement, apolipoprotein B, not just an LDL cholesterol reading. These are standard, covered tests, and they are the most direct available window into whether your liver's export mechanism is actually functioning. Part 2. The molecular shipping container and why it stops being built. To understand why fat gets trapped in the liver, you need to understand the structure of the VLDL particle itself, because it is a precision-engineered molecular vessel, and it requires exact raw materials to construct. Each particle is a sphere. At its center is a dense core of triglycerides and cholesterol esters, pure fat, completely insoluble in water. Surrounding that core is a single phospholipid shell, with water-loving heads facing outward into the bloodstream and fat-loving tails anchoring into the lipid core. This shell is what makes the particle water soluble. Without it, fat cannot travel through blood at all. Embedded in that shell is a single molecule of a protein called ApoB100, apolipoprotein B100. This protein is not optional. It is the structural backbone of the entire particle. Every single VLDL contains exactly one ApoB100 molecule. Without it, the particle cannot form. This construction takes place inside the endoplasmic reticulum, a folded membrane network inside every liver cell where protein synthesis and lipid processing converge. Think of it as the factory floor where these molecular shipping containers are actually assembled. The assembly happens in two steps. In step 1, as ApoB100 is being synthesized on the ribosome, amino acid by amino acid, an enzyme called MTP, the microsomal triglyceride transfer protein, begins loading triglycerides directly onto the growing protein chain while it is still being built. This simultaneous lipid loading is what allows ApoB100 to fold into its correct three-dimensional shape and survive inside the factory. If MTP is not active, or if the lipids it requires are unavailable, ApoB100 cannot fold correctly. A misfolded ApoB100 is immediately flagged, pulled back out of the endoplasmic reticulum, and destroyed by the cell's internal waste disposal system, the proteasome. The shipping container is demolished before it has been finished. In step 2, the partially assembled particle fuses with additional triglyceride droplets inside the factory lumen to form the fully mature VLDL, which then travels through the Golgi apparatus and is secreted out of the liver cell into the bloodstream. The entire process depends on the continuous availability of one specific molecule, and that molecule is the one the modern diet is most systematically depleting. Protocol: monitoring the assembly line. The most direct clinical proxy for VLDL assembly failure is serum ApoB100 levels combined with liver imaging. Low ApoB100 with elevated hepatic fat on ultrasound tells you that the protein is being degraded before particles can be assembled, the precise signature of a broken factory, not simply excess food intake. Track this every 3 months during active restoration to confirm the trajectory is moving in the right direction. Here is what makes this mechanism so important to understand. Your muscles and your heart are designed to run on fatty acids delivered by VLDL particles. When the liver stops exporting them, those tissues begin scavenging alternative fuels. Your brain interprets that scarcity as hunger. You eat more. More fat arrives at a liver that still cannot export it. The cycle tightens, the belly grows, and the hunger never resolves, not because your willpower is insufficient, but because your tissues are genuinely not receiving the fuel they were designed to use. Part 3. The missing raw material. Phosphatidylcholine and the choline crisis. The molecule that the VLDL assembly line cannot function without is called phosphatidylcholine. Phosphatidylcholine. It is the primary phospholipid in the outer shell of every VLDL particle. Without it, the shell cannot be constructed. No shell means no particle. No particle means no export. No export means accumulated fat. But phosphatidylcholine does far more than build the shell. It physically escorts ApoB100 from the cytoplasm into the lumen of the endoplasmic reticulum, the very first step of assembly. Without adequate phosphatidylcholine, ApoB100 cannot even enter the factory correctly. The process does not slow down, it does not start. Phosphatidylcholine also protects ApoB100 from degradation as it moves from the endoplasmic reticulum through to the Golgi apparatus. Without that protection, the protein is marked for destruction before it ever reaches the secretory pathway. And phosphatidylcholine coats the surfaces of lipid droplets waiting inside the hepatocyte, acting as a surfactant that prevents those droplets from fusing into enormous immobile globules that the assembly machinery cannot access. 4 distinct, non-redundant functions. When phosphatidylcholine is depleted, all 4 fail at the same time. The liver synthesizes phosphatidylcholine through 2 pathways. The first, called the Kennedy pathway, uses dietary choline directly. The second, called the PEMT pathway, converts a related phospholipid, called phosphatidylethanolamine, into phosphatidylcholine through 3 methylation steps, using a methyl donor called SAM. The PEMT pathway requires methionine, folate, and vitamin B12 to keep SAM regenerating. And research has confirmed it is specifically the phosphatidylcholine produced through this PEMT pathway that is most critical for VLDL secretion. Modern dietary patterns are depleting choline across entire populations. The adequate intake is 550 milligrams per day for men and 425 for women. The richest sources, beef liver, whole eggs, wild salmon, have been progressively displaced by processed foods that contain almost none. Clinical experiments have shown that patients fed intravenously with adequate methionine and folate, but zero choline develop fatty liver disease with measurable liver damage within weeks, and those abnormalities fully resolve when choline is restored. The mechanism is not associative. It is direct and causal. Protocol: phosphatidylcholine restoration. Prioritize dietary choline first. 2 to 3 whole eggs daily provides 300 to 440 milligrams. Beef liver at 3 ounces provides 356 milligrams. Wild salmon provides approximately 190 milligrams per serving. If dietary sources are insufficient, phosphatidylcholine supplementation derived from sunflower lecithin at 1,500 to 2,100 milligrams per day has demonstrated measurable improvements in hepatic lipid profiles in clinical trials through 2025. Support the PEMT pathway in parallel with methylated folate, labeled L5-MTHF on supplement products, and methylcobalamin, the active form of B12, to ensure the methylation cycle is not bottlenecked upstream of phosphatidylcholine synthesis. Allow 3 to 6 months minimum for measurable improvements in lipid panel data. Rebuilding phosphatidylcholine pools and restoring ApoB100 stability is a sustained biochemical process. Part 4. When the factory breaks under pressure. When phosphatidylcholine is depleted and ApoB100 cannot be properly loaded with lipids, triglycerides begin to accumulate inside the endoplasmic reticulum itself. The factory was designed to fold proteins and assemble lipoproteins. It was not designed to store fat. When it is forced to, the physical properties of its membranes change, the protein folding environment deteriorates, and proteins that were being built begin to misfold and pile up inside the lumen. This state is called endoplasmic reticulum stress, and it triggers one of the most powerful cellular emergency responses in human biology, the unfolded protein response. The UPR. This response is activated through 3 sensors embedded in the factory membrane: IRE1-alpha, PERK, and ATF6. These sensors signal the cell to reduce protein synthesis, increase chaperone protein production, and clear the misfolded backlog. In the short term, this is protective. But when endoplasmic reticulum stress becomes chronic, because phosphatidylcholine deficiency and lipid accumulation are ongoing, the unfolded protein response shifts from adaptive to destructive. The IRE1-alpha sensor activates a downstream kinase called JNK. JNK directly blocks insulin signaling in the liver by interfering with insulin receptor substrate 1, creating a state of hepatic insulin resistance that redefines the liver's metabolic behavior entirely. And here is the paradox that traps people for years. Once JNK-driven insulin resistance sets in, the liver loses its ability to suppress its own glucose production, so it overproduces glucose continuously, while simultaneously continuing to manufacture fat through the mTORC1 and SREBP1C pathways. The liver is being instructed to produce more fat, while it is physically incapable of exporting the fat it already holds. The warehouse fills faster than it was ever designed to contain. Meanwhile, the inflammatory signals from the unfolded protein response, through NF-kappa B activation, and the release of cytokines including TNF-alpha, IL-1-beta, and IL-6 directly suppress MTP expression and ApoB100 synthesis. What little VLDL assembly capacity remained is now being actively dismantled by the cell's own inflammatory machinery. The liver enters survival mode. Fat export is deprioritized entirely. Stagnation becomes the new biological baseline. Protocol: breaking the stress cycle. Eliminate fructose-sweetened beverages and ultra-processed foods. Fructose is processed almost exclusively in the liver and directly activates SREBP1C, the master switch for new fat synthesis, accelerating the rate at which the factory is overwhelmed. Reduce refined carbohydrates to below 100 grams per day during the active restoration phase. Add 150 to 200 minutes of moderate aerobic activity per week. Clinical data confirm it independently increases hepatic fatty acid oxidation and reduces factory lipid burden without requiring weight loss as a prerequisite. TUDCA, tauroursodeoxycholic acid, is a bile acid derivative with emerging clinical evidence of direct endoplasmic reticulum stress reduction in fatty liver models, currently under active investigation in 2026 trials. Consider this carefully. Your standard metabolic blood panel may look almost normal, while this entire crisis is unfolding inside your liver cells. Serum triglycerides may not be dramatically elevated, because the liver is not producing enough VLDL particles to push triglycerides into circulation. It is holding them inside. The very biomarker that should warn you the export system has failed may instead appear reassuringly low, while fat accumulation inside your hepatocytes continues to compound silently. This is why this condition is called silent. And it is why understanding the mechanism matters far more than waiting for your numbers to look obviously wrong. Part 5. The peripheral starvation driving your hunger. There is a downstream consequence of VLDL failure that almost never enters the conventional weight loss conversation. While triglycerides accumulate in the liver, your peripheral tissues, skeletal muscle, cardiac muscle, the diaphragm, are being starved of the fatty acids they were built to receive. Skeletal muscle preferentially oxidizes fatty acids at rest. The heart derives 60 to 70% of its baseline energy from fatty acid oxidation. When VLDL secretion falls, these tissues cannot receive adequate fuel. The brain responds to this peripheral fuel deficit by amplifying hunger signaling. Ghrelin rises. Leptin resistance, which coexists with hepatic fat accumulation, means satiety signals fail to register normally. The result is a state that feels like constant, unresolvable hunger inside a body that is, by every conventional measurement, eating more than enough. You eat. The fuel goes to the liver. The liver cannot export it. The muscles do not receive it. The brain signals hunger again. This is not a psychology problem. It is a fuel logistics failure manifesting as subjective appetite in a body whose supply chain has broken down at the molecular level. Protocol: peripheral metabolic support. Resistance training 2 to 4 times per week directly upregulates lipoprotein lipase expression in skeletal muscle, increasing the muscle's capacity to extract and oxidize fatty acids from whatever VLDL particles the liver does manage to secrete. This increases peripheral demand and reduces the systemic lipid burden simultaneously. Maintain dietary protein at a minimum of 1.6 grams per kilogram of body weight. Adequate amino acid availability independently supports ApoB100 synthesis and reduces the rate at which newly made ApoB100 is destroyed by the proteasome before it can be assembled into particles. Part 6. The Restoration Framework, Rebuilding the Assembly Line. The 2025 clinical literature has confirmed a specific biological framework for restoring VLDL secretion. A randomized controlled trial published in August 2025 in Therapeutic Advances in Chronic Disease demonstrated that phosphatidylcholine supplementation at 2100 milligrams per day produced significant reductions in total cholesterol and serum triglycerides at 3 months, with measurable reductions in LDL and VLDL and increases in HDL by 6 months. A 2025 review in the World Journal of Biological Chemistry confirmed augmenting phosphatidylcholine availability allows hepatocytes to regain their capacity to package and export triglycerides into circulation, alleviating intracellular lipid burden. And as that burden clears, endoplasmic reticulum stress resolves, the unfolded protein response deactivates, JNK signaling falls, insulin sensitivity is restored, and the inflammatory cascade winds down. This is the biological sequence of recovery. It has a realistic timeline. The 6-month arc seen in clinical trials reflects that rebuilding phosphatidylcholine pools, stabilizing ApoB100 synthesis, clearing the factory lipid backlog, and resolving chronic unfolded protein response signaling cannot be rushed. There is no intervention that collapses that timeline. But the mechanism of recovery is as precisely defined as the mechanism of failure. Full restoration protocol, 4 layers. Layer 1 is nutritional substrate restoration. Achieve 500 or more milligrams of dietary choline daily through eggs and animal proteins, or supplement with phosphatidylcholine at 500 to 2100 milligrams per day. Add methylated B vitamins, methylfolate, and methylcobalamin to ensure the PEMT pathway is not bottlenecked upstream. Maintain complete protein intake of 1.6 grams per kilogram of body weight to support ApoB100 synthesis. Layer 2 is lipogenesis suppression. Cutting off the internal fat manufacturing process, eliminate fructose-sweetened beverages entirely, and reduce refined carbohydrates below 100 grams per day, directly reducing the rate at which new triglycerides are being synthesized and delivered to an already overwhelmed factory. Layer 3 is physical activation, 150 to 200 minutes of moderate aerobic activity per week, combined with resistance training 2 to 4 times weekly. Aerobic work increases hepatic fatty acid oxidation. Resistance training increases peripheral lipoprotein lipase activity. Together, they reduce the supply-side burden on the liver while increasing the demand-side uptake of exported particles. Layer 4 is inflammation management, 7 to 9 hours of sleep per night. Sleep deprivation independently activates NF-kappa B and worsens unfolded protein response signaling in the liver. 3 to 4 grams of EPA and DHA combined per day through oily fish or pharmaceutical-grade fish oil. Omega-3 fatty acids have demonstrated direct suppression of SREBP1C-driven lipogenesis and measurable anti-inflammatory effects on endoplasmic reticulum. Stress pathways in clinical settings. The reason this protocol has 4 layers is that the failure had 4 layers. The factory did not break overnight. Phosphatidylcholine was not depleted in a single week. The inflammatory signaling that is suppressing MTP expression built over months or years of compounding deficiency. Restoring the system requires addressing every layer that contributed to the failure, not one supplement, not one lifestyle change, but the entire biochemical infrastructure of the hepatic export mechanism, rebuilt from the substrate level outward. The export problem nobody diagnosed. The belly fat that has resisted everything you have tried is very likely not a problem of intake, it is a problem of export. The fat is arriving at the liver is receiving it. The system designed to package it into VLDL particles and ship it into circulation as fuel, that system is failing at the molecular level. Phosphatidylcholine is depleted. ApoB100 is being degraded before particles can be assembled. The endoplasmic reticulum is under chronic stress, firing inflammatory signals that suppress the MTP activity needed to restart the assembly line. And visceral fat continues sending free fatty acids back to the liver through the portal vein, worsening every layer of the cycle. You are not failing the diet. The cellular infrastructure of your liver's export mechanism was failing, silently, invisibly, and for reasons that have nothing to do with how motivated you are. The solution is not to eat less and hope. It is to rebuild the assembly line, restore the phosphatidylcholine, protect the ApoB100, reduce the lipid burden pressing against the factory walls, resolve the unfolded protein response, give the liver the substrates, the metabolic conditions, and the sustained time it needs to transition from a congested reservoir back to the high-throughput distribution center it was always designed to be. When the VLDL export mechanism is restored, fat moves, not because you forced a caloric deficit large enough to overcome the blockage, but because the biological infrastructure that was always supposed to move fat has been patiently, systematically, and correctly rebuilt. That is what belly fat loss actually requires at the cellular level. And it begins not in a caloric calculator, not on a scale, but inside the endoplasmic reticulum of a single liver cell, where ApoB100 is waiting to be loaded. A phosphatidylcholine shell is waiting to be wrapped around it, and the outbound trucks are finally ready to run.